5 years old. We came from a group that was that started right before COVID called Women in Fracturing, but turned into the hydraulic. And we're all about anything fracturing, hydraulic fracturing in the oil and gas industry, as well as geothermal, and you name it. If it's hydraulic fracturing, we're all about it. Okay, you go there. Next slide. Um, Here, our mission is to primarily share knowledge. We want to share technology. We've got over 4,000 members. Last year we put on 14 webinars, two networking events, two special sessions, and three SPE live webinars. Okay, go ahead with the next slide shows that while I may be the chair, our efforts could not happen without all of these people. They are the backbone of our section, and this is how we actually get things done by this fine group of people. Okay. If you'd like to join, you can either go to the SPE website. Unfortunately, I think you have to be an SPE member, but you can use those QR codes.
Sorry about that.
Not a problem. Not a problem. Look forward to the talk.
Thank you, Steve. And our first speaker today, and Gordon, go ahead and share your screen if that's hopefully that's possible, is Gordon Pospisil. And Gordon is going to speak on moving beyond drill and drain to increase recovery in tight oil plays. Well, Gordon has over 40 years of experience in the oil industry in the Rockies, Alaska, Texas, Canada, Argentina, and Russia. He's been with Liberty Resources and BP Exploration, Atlantic Richfield, and Touche Ross and Company, now Deloitte. His extensive exploration and production experience spans prospect evaluation, field development, to designing and executing stimulations and enhanced oil recovery program. And he has financial experience ranging from reserves assessment through financial reporting, budgeting, and economic valuation. Underpinning all of this are degrees and a Master of Science in Petroleum Engineering from UT Austin and BBA in Accounting from St. Mary's University in San Antonio. Gordon is a registered professional petroleum engineer. Gordon, I might ask you to go to full screen if you could. And at that point, the floor is all yours. Isn't this the way it works? Well, maybe we can just minimize the size of the left-hand column and just go with this view, Gordon. I mean, it'll be fine. And you will have to unmute as well. There we go. See.
Okay, let's see. Not exactly clear why I've got trouble.
Well, why don't we just go with this? This will be just fine for the audience. People will
Okay,
get your message. Oh, there you go.
there we go. Okay, are we there?
Yep.
Okay, very
All
good.
yours.
Okay, with that, yeah. So, well, the obviously the theme here is hydraulic fracturing. I'm looking at the potential, obviously the opportunity to go beyond that as we focus around increasing recovery, and particularly from tight oil plays. My history is included, as you mentioned, a focus in terms of enhanced oil recovery. Uh, More recently, developing tight oil plays with hydraulic fracturing and long uh, extended laterals and that sort of thing. But the opportunity is there to dramatically increase and pursue a prize by going beyond the drill and drain of hydraulic fracturing. So with that being my focus. So I'm starting off by just highlighting the size of the prize here. This is a map that describes the work by the Bureau of Economic Geology to characterize the major oil and gas plays in terms of oil in place. And then through a study of the drilling practices over multiple years and assessment of longer term recoveries, we were able to come up with a forecast of ultimate recoveries from the major plays. And I'll just focus on here the Bakken, the Eagleford, and the Permian, which identified per this extensive review that there's something on the order of 3 trillion barrels of oil in place from these major basins within the continental United States. And with that, only about 2% has been recovered to date. And with the current practices, despite the drilling of hundreds of thousands of wells, we're on a path to recover less than 6% of the original oil in place. So just to put it in context, in the recorded human history, there's something on the order of a billion or trillion and a half barrels of oil that have been consumed. And so here in just these 3 basins, we've got over 3 trillion barrels in terms of an opportunity. And with that, again, despite tremendous resources and obviously technology that's been deployed and is being deployed, we are looking at a dramatic opportunity in terms of the remaining target. And this just highlights the more recent production from the major basins. About 2/3 of our U.S. production, around 13 million barrels a day, is associated with tight oil. And with that, you can see the Eagleford and the Bakken have matured, and with that are on plateau, and that we're rapidly arriving there in terms of the Permian. So certainly, we're seeing the limitations of the existing technology in terms of pursuing long laterals and extensive fracture technology to deploy it. So this really just points to the need to look at the next steps in terms of the recovery factor as far as a displacement process. And the positives are that we have a track record of success. We've been able to demonstrate that high pressure gas injection in a huff and puff scheme successfully increases recovery. And this slide just highlights the progress by EOG in particular in the Eagleford, where they were able to reestablish rates in these drill spacing units by repeated massive gas injection into the drill spacing units. And you can see the recovery of oil. Although what you see also is with each successive huff and puff cycle, a rapid decline. With that, the positives are they were able to, that is EOG was able to quote 30 to 70% potential increases in recovery. And with that, significant improvement. However, the costs were fairly massive. That is, they required high pressure gas injection with large compressors that introduced a high cost in terms of their activity, something on the order of $5 to $8 million compression cost per project. With that relatively high cost per well as far as the project cost. So with that, while they implemented a program across hundreds of wells, that's actually been fairly limited in recent years, again, because of the specialized equipment, massive amounts of gas required, and a relatively high cost. So with that, the other thing that came about or was apparent from this process was that it was relatively inefficient. You saw a fair amount of gas leak off the drill spacing unit. So essentially, the barrels of oil per gas injection was somewhat limited. So another positive opportunity or demonstration has been reported recently by Occidental. And this is just part of what they released in their most recent earnings, where they highlighted that they have seen an uplift of something on the order of 45% with the injection of CO2 across their portfolio in the Permian and the Midland. With that, they were able to generate something on the order of 20 to 35% internal rates of return. It was a huff and puff process, but it did require, obviously, CO2 source, typically from their CO2 pipeline and reservoirs. With that, included multiple injection cycles and injection period over a couple of years, where they were able to see a sustained uplift. Here again, we're limited in that we've got the requirements for a CO2 source, typically a pipeline, and of course, you're price limited on the acquisition of CO2. The other, for most operators, would be limitations associated with the metallurgy and then ultimately the processing of the produced gas to remove CO2 prior to sales. So this was not would not be an option for many of the operators as far as the tight oil plays, and highlights here that this is something distinctive that Occidental has been able to take advantage of. So in contrast, though, one of the positives that is fundamentally a characteristic of the tight oil plays is that you've got, well, a very tight matrix, you've got a very light oil, and then a rich gas. So this allows the typical produced gas to be miscible at relatively low pressures. And here's a slide that just highlights work by the North Dakota Energy and Environmental Research Center, which demonstrated that for the Bakken in particular, and as we've seen it in the Permian as well, that you can arrive at a minimum miscibility pressure using produced gas, which essentially has a high ethane and propane content at relatively low pressures. And here their testing procedure is documented, but is shown on the left. And then on the right, you can see a characteristic MMP with reservoir fluids for methane alone, something on the order of 4,000 PSI. But with the combination of produced gas, including ethane and propane, you see the produced gas has a very similar minimum miscibility pressure to CO2, something on the order of 24 to 2,500 PSI. So very encouraging as far as the EOR potential. So aside from gas injection, recently there's been a lot of activity, particularly by Chevron, reported in terms of the use of surfactants. We've known that surfactants can be helpful in hydraulic fracturing, and it has actually increased fairly dramatically to think up something on the order of 20% of hydraulic fracture stimulations in the Permian are now including the use of surfactants. So it's recognized that there is a benefit, with the potential to improve the wettability, in particular in the flow characteristics within the matrix. It's part of hydraulic fracturing. And then this highlights, there are a couple of papers here which document the path by Chevron and others, which have utilized CO2 and, surfactants in a huff and puff process. And this involves a relatively rapid injection, characterized 60,000 barrels of water, 2 to 6 gallons per thousand surfactant. And then, as you can see, a sustained flow back. So again, the positives are that we've got an enhanced oil recovery process, moving beyond drill and drain. However, in this case, we're limited in terms of it introduces a lot of water. So there's a need typically for specialized artificial lift. ESPs would be the most typical. You're going to handle a lot of water. And then there's, of course, the cost of surfactant per treatment. So the challenge is to find a process that recognizes or that deals with the mechanisms associated with both the processes. And here we're characterizing the opportunity for co-injection and essentially reducing the operating cost and project implementation. So I've got a chart here that compares gas injection as implemented in the past by EOG the high cost of the injection, a relatively long lead time associated with that, and some of the elements operational risk of dealing with high pressure at the surface. So key here is that by co-injection, you can actually, given the long depths or the high depths, typically we're looking at unconventional plays, which are something on the order of 2 miles deep. You've got an opportunity to use that vertical column with a co-injection process to reduce the injection pressure requirements at the surface. So essentially that reduces the equipment requirements and reduces the cost. Then through co-injection, you're able to get both multiple mechanisms, both gas miscibility, repressurization, and then the benefits of spontaneous imbibition or the associated benefits of surfactant. And then finally, as we've known from water alternating gas processes in conventional fields, you get an opportunity for mobility control by introducing a lower or a more efficient displacing fluid within the system. So here's just a set of work, and this has been documented in a referenced paper by Dr. Schechter now at the Louisiana State University. And what you're seeing here is a process which included core floods, and I should core flood in terms of the use of gas in a core situation, not in a typical displacement, but with a process where you're extracting through high pressure gas. So with that, you've essentially got a matrix or a core sample with surrounded by a fluid that's introduced at high pressure. In this case, we're starting on the left side, you can see with time, a movement and a displacement where in the upper section in particular, you've got the displacement of oil by gas and hence going to from a blue to a red type of color, and this over a period of time. And then with the introduction of a surfactant, you see the continued recovery through a different set of pore throats in the lower section, which was deemed to be a tighter section. So with that, you've got essentially the benefits of both the minimum miscibility pressure type of extraction from the gas, as well as an improvement in recovery through the surfactant mechanisms of a change in wettability. So this is a process that is now implementable within the field here using a co-injection process with a relatively small surface kit, again, because you've got the hydrostatic column of the water to take advantage of. You've got less surface kit requirement. You're able to inject both gas and water, typically in a range of 3 to 4 million cubic feet per day, 4,000 barrels of water per day on a continuous basis for a period of time through a set of cycles. And with that relatively small surface kit, you can see the image in terms of the applicability where the DJ at just over 6,000 or 7,000 feet, the Bakken at 9,000 to 10,000 feet. And of course, the Permian similarly would fall well within the range of your injection capability. And again, the key here is that we're injecting a rapid cycle of water and gas, which creates a hydrostatic column that allows you to inject into the reservoir, build pressure above the MMP, and create an effective displacement process. So this has been implemented on 9 different wells in 3 different basins, North Dakota, Colorado, the Niobrara, and the Midland in the Permian. With that, we've been able to demonstrate success in terms of showing incremental recovery on each huff and puff cycle. So with that, the key here as far as implementation would be, an efficiency. So with that, the challenge has been to utilize gas or utilize a huff and puff process, which is low enough cost, which can be executed in the field, and which generates enough oil. So this image shows the comparison of the reported data in terms of EOG and others as far as the implemented Eagle Ford projects with the most recent and with multiple trials in terms of a co-injection process in the Bakken and then more recently in the Permian. With that, you can see here on the left side, and this is a reference paper where the details are documented, an order of magnitude increase in terms of the efficiency. That is, you're looking at over close to 300 barrels per million cubic feet of gas injected versus something on the order of 30. So this is a key aspect in terms of making the process efficient and implementable. So with that, as we would expect, that the challenge is to scale this and to deploy this across multiple wells within a pad and across the basin itself. So you're looking at taking each well, that might be declining to moving towards, with the initial declines of 80%, moving towards economic limits and reestablishing pressure, reestablishing recovery within the entire drill spacing unit. And a key aspect in terms of field implementation is that you can rig up equipment so that you can cycle between wells. So if you think in terms of your utilization of your EOR equipment, your source gas and produced water, you can implement this on a continuous basis and simply moving from well to well. So in this case, the example would be we always have 4 wells on production with 1 well on injection, and you're continually utilizing and deploying your equipment and your resource. So with that, the summary would be that clearly, given the size of the prize, the EOR is a game changer for tight oil. And I think we could, those of us in the industry for a number of decades have seen the game changer that horizontal fracked wells has had. And this is the opportunity for how to take advantage of that several 100,000 plus well set out there to sustain production from that large resource. So just as an example, something on the order of with 3 trillion barrels in place, if we can increase recovery factor by 3%, that's on the order of 90 billion barrels, which would be twice the current U.S. reserves level. So a huge amount. Timing is important. Of course, wells, with our several thousand wells that have been drilled, a large number are moving towards economic limit and potentially coming offline, despite the fact that we've already got infrastructure to the reservoir, and typically we've got gathering lines and other production infrastructure. So to recap, this is a proven technology in terms of it's being deployed across a couple of fronts. So the challenge is to deploy it at scale, where essentially each of our drill spacing units ultimately should introduce this secondary, tertiary type of process. And we have identified low-cost methods that make it more available to a wide range of operators. And a key aspect of there, well, this could be deployed with CO2. The CO2 is not necessary. It's not essential to the process. So with that, I say thank you and open it up to questions.
Well, just maybe in that respect, Gordon, we'll run through each one of the panelists and then we'll move to questions.
Very good.
If that's all right. And
Yeah.
we do have 3 distinguished panelists. I failed to mention that, and I would like to introduce the second one, and that is Dr. Alexandra Hakala, and she is the acting director for the NETL Oil and Gas Center of Excellence in the National the National Energy Technology Laboratory, NETL. And Alexandra leads strategic planning and research initiative development across NETL, and in coordination with the Department of Energy Fossil Energy Headquarters. She leads multidisciplinary geoscience and engineering research teams that perform R&D on the development of natural resources for sustainable energy and critical energy extraction. And she serves as NETL's representative to the DOE's National Lab Chief Research Officer Group. Now, before becoming a senior fellow, Ali's research focused on geochemical reactions and the behavior of naturally occurring geochemical tracers in oil and gas, carbon sequestration, geologic carbon storage, and geothermal reservoirs. She became a federal scientist at NETL in 2009 after completing a postdoc appointment, also at NETL. She was an Oppenheimer Science and Energy Leadership Program Fellow in 2023 and the recipient of the Presidential Early Career Award for Scientists and Engineers in 2017. Her Ph.D. is in Earth Sciences from the Ohio State University, and that was in 2008. And she has a Bachelor of Arts in Geosciences with focus in environmental studies from Princeton University in 2003. And as you can see, Dr. Hakala today is going to speak to us on geochemical reactions affecting shale fracture permeability. Ali.
Great. Thank you very much, John. And thank you, Gordon, for that excellent presentation just prior. The work that I'm going to be speaking about is work that was performed, it was maybe about 6 to 8 years ago. And the Department of Energy had a focus on understanding fundamental properties and let me minimize this so you can see it. Okay, that's better. The Department of Energy had an effort focused on understanding the fundamental properties of shales that were undergoing hydraulic fracturing. And the portion that I focused on, just based on my interest in geochemistry and some of my technical background, was trying to figure out what type of chemical processes are happening that might affect what's happening along shale fractures. We want to be able to get the hydrocarbons out, and also whatever happens along that fracture surface is going to impact how much material you can then also get out from the matrix through diffusion. So I think some of you might be familiar with the National Lab Complex. I just wanted to show you that we have a lot of sister national labs that focus on different areas of energy and national security topics. NETL, we have historically been focused on fossil energy. We recently went under a realignment with the Department of Energy under Secretary Wright. We are now called NETL is now affiliated with the Hydrocarbons and Geothermal Energy Office. And so our research at NETL also is moving from more of a capability-focused R&D, where we were organized according to Geosciences, et cetera, to having centers of excellence that are now focused on our primary energy resource types from the subsurface. And so that's where we're going to be having a very direct focus on understanding oil and gas. I am happy to be a point of contact to help you connect with our research teams at NETL and across the labs, because I think a lot of the capabilities I'm going to be talking about here, I'm hoping that they can help bridge knowledge gaps that are associated with seeing processes in the field and then trying to understand some of the technical details behind them. So NETL, we actually have 3 sites. The Oil and Gas Center of Excellence is at our Pittsburgh, Pennsylvania site. We had a question once, why aren't we in Houston? And it's just because of the historical DOE investment in certain locations. We also have facilities in Morgantown, West Virginia, and Albany, Oregon. Morgantown is our center for coal, and Albany is our center for critical minerals and alloys. So looking at the problem, many of you are probably familiar with the DOE oil and gas field labs that were active a few years ago. I'm showing some data here on the decline curve and then overall gas produced from the Marcellus Shale Energy and Environmental Laboratory wells located in West Virginia. And as we were looking at, as we look at these data sets, we see that you have some type of decline and then some type of activity happens to try and get the reservoir going again, a shut-in or some type of stimulation. And then you have a typical curve development takes place. And some of our colleagues at Los Alamos National Lab took a look at this question from more of a fundamentals properties perspective, where they are trying to understand if you just have the advective flow going through your primary fractures, or if you have some combination of advection and matrix diffusion, how do factors such as permeability then affect what's going on in these situations? And it turns out that really small changes in permeability can have a really big impact on what you're able to produce. So getting back to the geochemistry, we started trying to conceptualize, and this is Ali's cartoon from many years ago. This probably needs to be updated. But I as a geoscientist, I like to draw cartoons to try and think of what's actually happening as we're trying to stimulate a reservoir. You're trying to make some space. You're trying to clean up that space with the acid pack or a similar technique. Then you have some injection of your proppant and fracturing fluids in whatever scheme an operator decides to pursue. And then there's a period where you're expecting flowback and production to occur so you can actually produce your fluid, your hydrocarbons. And coming from a background of organic and redox geochemistry, and also having spent some time looking at mineral reactions, we started, I and the team at NETL started thinking, well, what are some of the chemical reactions that are going to impact what happens along something like this major flow pathway along a fracture, or even the reactions that then impact what the surface looks like. So if you're trying to get hydrocarbons to diffuse out of your matrix, that, are we opening up space? If we prop it open and if everything looks great, is there something happening at the surface that then prevents that porosity to maintain some openness to get the other fluids out? So this is a little bit of a complicated scheme, but I just wanted to show that how we started thinking about this overall picture. And I think you'll get the recording of this. We have a publication that describes this in detail, but we started with a very straightforward concept of what is actually happening in the reservoir that then impacts the chemistry of the solids and then the fluids that we see produced from the reservoir. So we tried simulating just benchtop lab experiments at different pressures and temperatures. What does the fluid look like when you're injecting something that has a composition similar to a 9-to-1 frac fluid and brine? And so the composition we worked with in this study is here on the right, just to give you a picture of a snapshot of how the Marcellus was being treated at the time. We got these data from some of our colleagues at one of the local operators in the Marcellus. And one thing I'm going to be focusing on in this presentation on what happens to the rock, but I wanted to put this on here just to point out all of the different areas where differences in pressure and temperature, fluid composition, and surfaces can have an impact on the overall ability to produce from a reservoir. So even if we might get our system right within the rock, we still need to get it out through the pipe here. And just wanted to point out that we have some experience with this at NETL as well, if there's any interest in follow-up in the future. But to look at some of the results, what you're looking at here are scanning electron microscope images of a pre-reacted surface of shale. That would be this A, and then a post-reaction here, B. For scale, this is a 20 micron scale bar at the bottom here. And I want to point out these numbers, 1, 2, 3, 4. In the pre-reacted, you can see these areas have some type of material based on the energy dispersive spectra that shows that this is carbonate mineral content. That's all dissolved here after we expose the rock to fluids. And so we are seeing that we have this dissolution of primary minerals. But when we took a closer look at some of the samples, we were able to see evidence for secondary precipitation. And so this started making the geochemical story a little more complex. We have some iron oxides that we're depositing, some new calcium carbonates depositing. We even saw flakes of barite. And then the Marcellus has some challenges with barite. There's a lot of barium in the reservoir fluids, and depending on how much sulfate's in your injected water, you can end up with some challenges. So we started focusing in on this question, because if you're able to dissolve material and then reprecipitate it, this becomes a very interesting geochemical system that then factors into, if we're trying to get these even just small percentages of increases in recovery from a system, if we understand these geochemical processes, that might be able to help us better manipulate either the process by which fluids are injected, or what's in the composition of the fluid, or both. So our experimental setup involves a core flood system. And so this is a benchtop experiment. These cores range anywhere from around 6 to 10 inches long. I don't have the diameter here, about a few inches diameter. I don't have the scale on this image, unfortunately. But these are artificially fractured using a Brazilian technique just to create the fracture. You end up with 2 slices that then we sandwich back together to put into a core holder. And then we have injected fluids that are based on the type of reactions we're trying to understand. And then we have an ability to sample the fluids. And then after the experiment, we have the ability to look at the surface of the fracture. And then we do try to get some cross-sectional details. I don't think I have it. I don't have it in this presentation, but this is where our collaborations with our national lab partners are really helpful in working with the Slack lab. We were also able to apply some synchrotron techniques to look at more fine-tuned details of the chemistry. But today I'm going to be focusing on the barite question because it provided some really exciting and visible results and potentially impactful results. So what you're looking at on these are computed tomography images. So we're able to perform the experiments in our core holders, and then we pull the core out of the fluid flow experiment, and then we put it through. We have a series of CT scanners ranging in resolution. So this is from our industrial CT scanner, where we're able to put the core holder in and take a look at what the sample looks like before reaction. You can see there's a fairly clean surface. Wei had highlighted pyrite on this image, just she wanted to show where some of the potential reactive iron species might be present. And post-reaction, this is looking at a 4-day reaction, 21-day reaction. There's development of barite along what is this primary flow pathway here. There's some change in the longer term in some of the areas that weren't part of the primary flow pathway here. You can see in this cross section where you have a lot of space and maybe not as much space over here. So this gave us some idea of along these major flow pathways, we're seeing a lot more deposition. It is possible, so a possibility being if you're trying to access these large flow pathways to get more hydrocarbons out, there could be some issues or challenges in being able to control flow from the matrix. So our team, this is Dustin Crandall, leads this team looking at how we actually calculate some of the flow properties. To orient you on this figure on the right, on the top, you're seeing images that just show the calculated flow magnitude in milliliters per minute along different portions of that fracture face, both during the stimulation. So this would be when we have fluid actively flowing through the core setup, and then during shut-in, where we allow the fluid just to sit within in the core in the experimental setup. Images C and D below are the same as A and B above. So A correlates with C, B correlates with D. The difference is that the coloring of the flow magnitude is different, just to better highlight where you have really high flow is where you also then see this barite show up fairly high barite thickness here. And when we going back to drawing some cartoons, we started developing a conceptual model, and this is again focused on the Marcellus, where there are a few different there are two main chemical reaction areas that we considered are important in this system. When you're injecting or in arid regions of fast flow, the barite nucleation is occurring in the fluid and then depositing on the surface. So this is where it's in considering what might be impacting my primary flow pathways. That's where the injected fluid chemistry really could have a huge impact because it's nucleating and then depositing. During shut-in is where there needs to be some thought about what's controlling the barite precipitation. And in that more static scenario, or I guess relatively static scenario, the rock itself is going to be controlling a lot of the reactions that are occurring. And then that's where you might have some reaction more into the matrix and other parts of the rock. So so this was a fairly high level and quick example with one reservoir. But the main point is that in thinking about how we want to maximize recovery, and if we're trying to access different parts of the reservoir in a more efficient way, some of these chemical processes may have an impact and are some things to consider in designing some of these novel processes, including things like surfactants or different types of fluids that are being injected, and also in the different types of orders. And just coming back to my geochemical roots, I mean, it comes down to pH and redox chemistry, and we're trying to understand how the reservoir is going to behave geochemically. So we have some evidence in seeing that the expectation is that the pH, after going through all the dynamic changes during fracturing, frac fluid injection, and then production, we've seen in a number of experiments that the pH tends to get back to some type of steady state over time, just because of the mineral reactions and fluid mixing. Something that we haven't really been able to probe in detail, which could be impactful, is understanding how oxidation and reduction conditions affect these reservoirs. I mean, these are reduced reservoirs. We're injecting fluid that may or may not have redox controls. It is what we're expecting to happen in the reservoir. What is happening, because you might have some of these additional electron transfer reactions happening that can again affect mineral reactions, but then also some of the organic reactions as well and behavior. So I just put this up here for a consideration in thinking about the reservoir from a geochemical perspective. Oh, and with that, I will conclude my comments and turn it back over to John.
Thank you, Ali. So we've had two distinct presentations so far, and our third is going to be given by Kevin DeLapp. And Kevin is going to speak on Eagleford Huff and Puff EOR single well pilot with large Y-grade injection volumes. Now, Kevin is the Vice President of Reservoir Engineering for BlackBrush Oil and Gas, LP. He has 20 years of oil and gas experience in both public and private sectors, and this includes a diverse background, strategic planning and partnerships, acquisitions and divestitures, reserves evaluation and estimation, EOR Huff and Puff, planning and execution, as well as public and private reserves reporting, finance, accounting, midstream, downstream, and land. So Kevin really has a broad portfolio, and he's held previous position of strategic development and reserves director at Exco Resources. He also served as senior business development and strategic planning representative for JW Operating Company. And so with that, Kevin, the floor is yours.
Okay, thank you very much, John, for the introduction, and thanks, Ali and Gordon, for your presentations. It's always good to kind of get into some of the technical weeds, which I'll have some of those as well here. So, as John mentioned, as a generic intro to our project, we would first start with kind of the geography. So our asset is the Chittum Lease asset, which is in the very shallow portion of the Eagleford. It sits in the Maverick County and very southwest Zabala County area of the play. So one of the struggles for us to date, we've, with all of our primary production efforts, have really had tier 2 results up until the time that we had spent designing our Huff and Puff pilot, which we will get to here in a bit in more detail. But the biggest distinction between a lot of the other kind of field gas injection projects or CO2 injection projects is the source of the injectant for us. So through our founders running kind of multiple companies, there is a Y-grade line that goes from the Permian directly through our asset. And we did that on purpose so that we would have this Y-grade injectant available as a potential source for our Huff and Puff project. And so we spent about 3.5, 4 years on the design work and ultimately implemented. But the need of that is because of the shallow nature of our reservoir. All of our existing wells are at, in terms of just true TVD, are at 5,000 feet plus or minus, and with relatively low reservoir pressures. And so what would happen for us is we'd go out, drill and complete a well, spend about 20 days flowing back only water, 40 plus days to get to IP. But by the time we'd gotten to IP, we'd lost 90% of our flowing tubing pressure. So despite having an extremely high resource in place, almost 2 times that of what our position was in Karnes County, we were only able to produce tier 2 results. And so what does that look like from a characterization standpoint? Our porosities are in the 15 to 18% range, with the lower Eagleford being 180 to 220 feet of thickness and relatively low API gravities, on average right now at about 36 of our producing wells. Well, despite all that, again, there's this 68, almost 69 million barrels of oil in place per section, which was the size of the prize. So similar Gordon and Ali's presentations, for us to even move that recovery factor, even 1% was going to make a very big impact on our results. And so our thesis going in was to take one of the analog areas where we drilled and produced for years, one of our core assets in Karnes County, Eagleford. But that was much deeper, right? You're talking about 12,000 feet TVDs with much higher initial pressures up in the 8,000 PSI range, which our initial tubing pressures at Eagleford are 2,700 pounds to 3,000 pounds. So much shallower, much lower pressure. Because of those reasons, to date, if we were to apply the same spacing assumptions that we routinely developed in Karnes, we're only estimating a recovery factor of 5%, which, again, is not horrible, but we're having to achieve that through very tightly dense well spacing. Anyways, that is our size of the prize here, taking something that has almost 2 times the oil in place and really chasing that with this Y-grade pilot. I won't spend too much time on this since most of the folks on the call probably understand what a huff and puff is, but in our case, we have single isolated well bores. These are not pads. These are not, east-west offsets to each other. They're sister wells going north and south on a heel-toe basis. And so we're injecting thousands of barrels of Y-grade. When it hits the first set of perfs and clusters, it's feeding out into the reservoir until that pressure kind of forces it down and kind of what I call this reverse limited entry to fill up all of our now producing stimulated rock volume from the initial primary. And so one of the benefits to our method is that we are using Y-grade, which is first contact miscible. It has a vapor pressure of 450 PSI. So if you want to think of that in terms of GPM, we are injecting something that is, a 28 GPM versus our field gas in the area is about 7.5 GPM. So as long as we keep it under pressure, as we've done, it's staying as a liquid. And so that's an improvement upon some of the field trials that an EOG or others have done who, as Gordon introduced, have to use these very highly spec'd compressors. Like in EOG's case, because of the depth and temperature in Karnes, to reach minimum miscibility pressure with field gas, which is very high in methane, they were having to pressure up to this 7,000 PSI plus. In our project, the minute that Y-grade hits the reservoir, it's instantly mixing with our native reservoir fluid. And so what is it doing? It's changing the viscosity. We're obviously pressuring the well up. And so the first really recovery mechanism is taking something that's very heavy oil, lightening that load, thereby reducing the pressure requirement. And then illustration 3 here is just a cartoon to show kind of the diffusion contribution, the mass transfer mechanism of our project. And you can think of that as displacement as you want, but ultimately we're diffusing out of the matrix and gaining access to previously inaccessible hydrocarbons. So what did this look like in practice? So this is probably our favorite chart. So both of these charts are on the identical y-axis. On the left-hand side, you see the entire 7-year production history of this well. What you don't see at kind of negative time 0 is that time spent just unloading water. And even at its best on a single day IP, which happened, by the way, on artificial lift, we had a single day, 24-hour period where we produced 760 barrels a day. Falls off very quickly because of that lack of pressure and hangs in there, for a good long while. We were at 18 barrels a day prior to our injection pilot. We inject through 3 cycles. It was always planned to be 3 cycles, 3 injection, 3 production cycles. And we were making improvements and modifications along the way as we learned. But our most optimum cycle in terms of the gas handling equipment at surface and getting the volatility under control of the crude was actually this 3rd cycle. One of our favorite stats is that for a 5-day period in cycle 3, we averaged over 1,000 barrels a day. Compared to in primary production, we had a single day IP of 760 barrels a day. So For us, that was a 56x increase in our baseline, which was obviously a pretty good breakthrough, and what we had hoped to achieve. And why did we achieve what we did and all these things? Part of that's reservoir quality, right? Having so much oil in place that you're gaining access to. Part of that is utilizing a very powerful solvent in the Y grade. It's about 45% ethane, 25 to 30% propane, and then it has some additional intermediates there. Really tops out in terms of meaningful contribution in kind of your C5 range. Have some reference material down here at the bottom left, but the next slide we wanted to show was, so this was the rate time effect. So what was the effect on the EUR? Well, because we were using a Y grade that is, an unfractionated mix of NGLs, we obviously have to do this through all this work in terms of the pre-pilot and post-pilot through the use of a compositional simulator, because we are having to track the compositional exchange between native fluids, tracking our networking injectant, and then also being able to allocate that on a go-forward basis. So we spent, as I said, about 3.5, 4 years on the pilot design, modeling all the ins and outs, testing, retesting all of our assumptions, asking tough questions of our partner and consultant who helped co-develop this compositional model. So ultimately, we went to the field trial. So if you were to think of this primary EUR as like a 20 to 30 year just traditional decline curve analysis EUR, this well, which was a 4,500 foot lateral, would have been about 190,000 barrels. After the pilot, taking all of that real world empirical data and recalibrating to it, we are now targeting over 500,000 barrel EUR. So if you were to take this primary EUR and cut that to 10 years to kind of make it more apples to apples, that's achieving a 4 times uplift in our EUR from our primary. Some other commentary, we've worked with lots of experts in the field. A lot of you on this call, I'm sure, are familiar with Dr. Kwok Win, who is the UT professor and spent his entire career in tertiary recovery. And, in terms of North America, has certainly probably been involved on the vast majority of projects. And he's on record that's saying that this is one of the best results he's seen in kind of the certainly the huff and puff world, if not the tertiary recovery landscape. Another opinion is just similar. It's International Reservoir Technologies, who was our partner that co-developed this compositional simulation. They've said the same thing in terms of their project. It's one of the best results that they've seen to date. And then in terms of a third-party opinion, DeGloria McNaughton has been our third-party reserves assessor for many years now. We gave them all of our data and asked them to give us a most likely case and an upside case. The most likely case you can see came in very closely to the fully calibrated compositional model, and their upside case is obviously for a single well that's a 4,500 foot lateral, puts quite a carrot out there for us to chase. And the way I like to think about that is, what if our Y grade injectant is more efficient over time than what we've seen to date? And so if instead of getting a barrel in, barrel out, what if you got 4 or 5 barrels in for every, or 4 or 5 barrels out for every barrel that you put in? So some of the lessons learned, we had what I call this Goldilocks scenario. We are structurally simple in Chittum and the Eagleford, so we didn't have a lot of thief zones in terms of big complex faulting. That's containment is something that all operators who are doing EOR fight in terms of if they're just specifically doing field gas. So you don't want to have these leak off points so that you can reach the miscibility and get out to the farther reaches of your simulated rock volume. But you also don't want, to have an immediate pressure out, signaling either skin damage or a smaller SRV than you thought you'd had modeled in the first place. And so one of the other things that we learned was that cohesion is a real engineering principle. So whereas our Y-grade mix, as I mentioned, was 45% ethane, the flash point of ethane, or the vapor pressure of methane, is obviously very high. And you would think of, in terms of, if it was just by itself, it should be breaking out of the oil relatively easily. But at our HP separator that we put in, trying to be thoughtful about getting a big, kick of gas to help our crude volatility, we actually never saw it. So our Y grade and native were really wanting to stay combined at kind of that molecular level. And so only until we put in additional instruments of processing, like, a couple line heaters, things of that nature, do we really get to the desired breakout. Now, that's a good news and bad news. It was good news in terms of the arbitrage opportunity. The more we tune that on a go-forward basis of this Y grade to stay miscible and be sold as crude, we'll take that exchange any day of the week. You're buying something at $25 per barrel, and we used to say the term selling it at $70 oil, but oil's obviously taking a little run here. So in terms of the just the allotted time here, there's obviously a lot of time spent in multiple phases of this. We did geo fingerprinting, looking at carbon isotopic concentrations to really make sure that we had a great understanding of what that allocation looked like and what that fluid exchange looked like. And have a couple of go forward projects that will really make this Huff and Puff drive on a long-term basis. But I'll pause there because there'll probably be some questions that can tee me up for some of those answers later.
Thank you, Kevin. And three fantastic presentations. The protocol now is that we'll go back to the start, and I'll pose two questions to each of the panelists, and after they've answered those, we'll turn it open to the audience. So Gordon, let's start with you. So what do you see the barriers that are preventing more operators from implementing EOR for tight oil plays to increase recovery?
Sure. Yeah. Thank you for that. So first off, I think the barriers are just part of it is just the opportunity that hydraulic fracturing and horizontal drilling has presented. When you can create new wells, you've got kind of an expanded resource base of targets. I think the focus has clearly been on holding acreage, on establishing, the optimized development scheme in terms of initial drilling. And we continue to see, for example, I worked with Liberty Resources, and we went from 2-mile laterals to 3-mile laterals. And of course, now we're moving to 4-mile laterals. We're optimizing, all the elements of hydraulic fracturing, and you're seeing the results, both in efficiencies and with wells that come on at 1,000 barrels a day. So I think that priority, that focus has been part of the, let's say, the distraction from looking at enhanced oil recovery. The other is, unfortunately, enhanced oil recovery, and I've been in this business of promoting enhanced oil recovery projects back to my Prudhoe Bay days working in Alaska, is that there's a bias that enhanced oil recovery is a expensive and delayed return process. And of course, a lot of the private equity backed and even the majors have focused on high returns through the high rates that can and high value that can be developed through horizontal wells with fracture stimulations. A key with the Huff and Puff scheme is, though, it's more like a well treatment. So it's literally like taking a low rate well and stimulating it back to its original higher rate. So the return can be at the front end. And I'd say the economics, if implemented properly, in tight oil Huff and Puff schemes, can be much more favorable than the understanding is. And with that. And then the third point is the operators need to move towards where enhanced oil recovery is a end has part of the original design, is integrated within the original design and development scheme. And that is in terms of the artificial lift selection, the ability to convert wells from primary to injection and then back to production. So I think it really just comes down to a slightly different focus and a recognition of the opportunity size.
So maybe I can just get you to recap on that and be a little more specific, or just specifically recap on that. How can these barriers be overcome?
Sure. I think the recognition of the success that we've seen with gas huff and puff injection, the combination of water and surfactants to utilize the efficiencies that have been demonstrated in pilots can identify that we've got a process that can deliver barrels at well below $20 a barrel, even down to about $10 or $15 a barrel. So much better opportunity to deploy capital and resources through enhanced oil recovery of existing wells than to drill new wells.
Thank you, Gordon. We'll move on to Ali. Ali, excuse me. So you talked about one particular reservoir. How do these processes change in different reservoirs?
Right. So I spoke about the Marcellus. We saw a lot of exciting chemistry there. We did similar tests in the Wolfcamp and nothing happened. And so it really does come back to the rock fabric. So understanding your reservoir, even understanding subzones within that reservoir will be important. And so if there are operational issues at play and you think everything is uniform, there could be some type of difference in what's happening chemically in certain zones. And so we found in systems where you either have a lot of potentially reactive components in the fluids, for example, the barium and sulfate in Marcellus. It's a challenge to control if you're not paying attention. And on the flip side, the carbonate mineral matrix can have an impact in terms of where you might be generating porosity to be able to access more of the reservoir into the matrix. So really understanding the rock fabric and some of that potential reactive mineral chemistry will be important.
So let's move to the other side of the spectrum. We have the rock. What about the fluid and the treatment itself? So how can injected fluids, proppant design best support increased access to matrix pore space in the reservoir?
Right. That's where you have to think about how the fluids that are being injected, how are those fluids potentially impacting what you've spent a lot of energy and resources to create in terms of a fracture matrix. So it does make sense to think through, do I have the appropriate chemical scheme for being able to ensure proppants stay where I want them to stay? Do I think that my surfaces of my rock are able to support the proppant? And are there different treatments that I can do to make sure that we can maintain an appropriate contact between the proppant and surfaces? Even the proppant type in terms of where it can access. Is it sand? Is it some of these newer carbon-based materials? Can those enable you to tap into different components of your reservoir based on your mineralogy and fabrics? So that's where I'm seeing a lot more of a tailored, like this is the appropriate scheme for this type of reservoir thought process. I've seen that evolve over the past 10 years. I encourage that to continue because now that we now have advanced computational techniques and we can now start pulling all these data sources together in new ways, we can start thinking of new schemes on how to continue on that improvement process. Even just the presentations we saw with the EOR during the session, just these nuances on how fluids need to be treated with these specific reservoir types. It takes a little bit of extra effort, but I think once you understand your story of the reservoir, you can continue moving in that direction.
Yeah, I think that's a really great message. So Kevin, your turn. What are the next steps for your project?
So you'd asked this to Gordon as well in terms of, kind of echoing the challenges so we've gotten a good result that we're obviously excited about, but there's always that fear of having a really great technical result and then not being able to make it an economic result. So a lot of our time here recently been spent modeling a Y-grade recovery and recycle system, so that we don't have to buy any more Y-grade than is necessary. So there's always going to be some of your injectant that's retained, and I kind of refer to that as like the networking injectant. But over time, what we've seen is that you start to get a very high efficiency in terms of a barrel that you inject, you can roughly get a barrel out. And if that's the case, then you need to be very thoughtful and considerate about how you are going to capture, separate, capture, and recycle that Y grade. So those are our immediate next steps. We're working with a midstream provider. We are probably within the next 30 days going to be finalizing a new venture to put that together. So that's really the next steps for us. And I would say even combining with that, we don't think we're 100% of the way there in terms of our injectant composition, optimization, cycle times. I teased with some cohorts the other day. I wish I could run 100 different simulations a day to kind of get to what might be the most optimum answer, because there's almost an infinite amount, along with some other kind of ad hoc potential accretive solutions like surfactants and things that we haven't gone down that path as of yet, because our solvent and injectant has done a pretty good job to date. But those are kind of our next steps as we look forward.
Well, I think you've kind of answered my next question, was what sort of optimizations, and you've mentioned simulations, surfactants. Anything else that you would consider for optimizing your process?
Yeah, I think for us, it's our near-term focus will definitely be on the composition of our injectant, and the efficiencies on a per barrel basis, kind of going up and down that scale versus where we started. So we started with we felt like had a good understanding of the need of what I refer to as kind of the fill up of the reservoir. And then, but, does that mean we were optimum? That still remains to be seen.
Okay, thank you. Well, now we'll open it up to questions from the audience, and I'll go through the questions on the chat. And surprisingly, the first question is from Gordon. So, Kevin, do you have an estimate of the process efficiency with the Y-grade injection?
So yeah, Gordon, you meaning in terms of like a measured efficiency in terms of a barrel injected versus a barrel extracted?
Yes, yeah, that's what I would think of. For example, with us, we would estimate that process efficiency of co-injection is around up to 300 barrels per million cubic feet of produced gas injected.
Yeah, so for the way I think of that term is, or the way we've made sense of it in our own heads, I'll put it that way, is that we kind of reach a maximum net injectant of about 120,000 barrels of Y grade up through our 10-year injection cycle. And that's to be offset by an increase or gain in our EUR of that 555,000 barrel EUR. So, if you want to take the primary minus those, minus the I'm doing some math in my head here, but that's like a 3.4 times barrel efficiency on our Y grade. So in other words, for every barrel of Y grade that that is a net working barrel, we get 3+ barrels of new crude out.
Thank you.
So we have a couple more questions for Kevin. Kevin, what is the order of magnitude of your permeability that you're dealing with, and the absolute permeability?
Very low. So we're kind of in this plus or minus 200 nanodarcy permeability.
And then Steve has another question for you. During injection, did you see any effect on the offsets?
No, we did not, and primarily, somebody mentioned this, maybe John, it was you or Gordon, but to date, our development has only been heel-toe offsets, so no direct east-west offsets. And in terms of our go-forward development plan, we are beginning with the end in mind. So we are going to start, as I mentioned in farms, we got as tight as 300 to 350 foot spacing. But here we are effectively doubling that. Our initial approach will be to start at no closer than 600 feet on development, because we want each of these wellbores to act as their own self-contained system to better affect the mass transfer component of this on a go-forward basis. And so that's kind of how we're looking at the development plan. As we drill new wells, those new wells are new inventory for our Huff and Puff program, and we hope to prove that maybe we can get tighter than 600. The oil in place would obviously support that, but for now, that's kind of the path forward. And so no communication to date. We hope to really limit that through our development plan.
And so here's another question for Ali. How can we monitor which chemical changes occur during reservoir stimulation, flowback, and production?
Yeah, and the monitoring is a big deal, and especially in real time. And some more recent discussions with colleagues, the ability to say I've monitored this parameter and it's telling me exactly what's happening in the reservoir. There's still a disconnect there. There are some opportunities to install things like fiber optics during the well placement, but that can be pretty expensive and has to be done from the start. Some of the areas that we've pursued, considering a well that's already in place and monitoring over time, are applying different geochemical tracers. And it's not injecting tracers, but it's having that understanding of the system to know, when I see this transition between some of the major divalent cations, that might tell me that a particular process is happening in the reservoir and I should pay closer attention to it. So I think there's some effort that can be done through looking at the chemistry of your flowback and then into longer term, the produced water, that can give you some insights on what's happening in the reservoir. I mean, it's going to be reservoir specific, but at least you can track the major mineral reactions, and then you can get some idea. If you go another level and start applying isotope geochemistry, you can get some idea of which minerals are reacting, or if you're getting introduction of fluids from other systems, like through a frac hit or through something else.
So here's a question that any one of you can take a stab at. And has there been any consideration of the effects of nanopores on component behavior in the computational modeling or in experimental work? Any comments on the possible effect of nanopore confinement would be appreciated.
Yeah, I'll comment in terms of we found through the CT scanning of tight matrix, in this case, Wolfcamp B, that the obviously the capillary effects are a significant feature, and that's where surfactants come into play, and can change that. Obviously the flow characteristics of that very tight matrix. So, and nanopores create essentially capture the oil where they're predominantly oil wet. So if you can change the wettability, through the injectant chemistry, you can improve ultimately the recovery.
Anyone else want to add to that?
I'd just like to second that. One of our colleagues at NETL is looking at those types of processes experimentally, and there are some pretty big changes that you can see with what's produced and what access the nanopores you have through surfactant or other fluid application.
And so the next question, any one of you can take a crack at, it's from Francisco Fragachan. How can we integrate some of these ideas into an IOR process versus an EOR process? For example, integrate into ongoing hydraulic fracturing operations.
I'll take an initial stab. So, I think for us, to give one example, is we feel very passionate about following on quickly for our huff and puff process after primary production. Now, that's a little bit reservoir driven from us being low pressure. So, when we are done, kind of getting our first recycle facility up and running for the existing wells, when we drill new wells in a perfect world, we're going to be following that up very quickly in as little as 90 days or less with our Huff and Puff project. And so I think for us, we're going to be very conscious of, what additional improvements we can make. One of which that we haven't spoken to today, but uh, we were I say bold, and I don't mean that as a compliment to ourselves, because sometimes I think we were crazy, but we did a pure hydrocarbon frac using modern proppant and development loads, and but all condensate and Y grade, so no water. And so there was some wettability, relative perm items that we were, hoping to kind of prove out. But for us, when we tack on to that a huff and puff process, we are curious ourselves to learn, did 1 + 1 = 3? Instead of 1 + 1 = 2. So a couple of comments, at least from our perspective.
Yeah. Um, there is another question for Gordon. Just clarification. Was it Wolfcamp sand or shale? Is that
Oh, we have Wolfcamp, the Wolfcamp reservoir target anyway, Wolfcamp B.
Wolfcamp B? And then a question from Kevin for Gordon. I mean, I wish it gets you guys together. So what is the sequencing for the co-injection process, i.e. water and gas injected?
So literally, it's a process of simultaneous injection where you've got a rapid switching between the gas. If you can visualize just literally a surface equipment with two lines, gas and water, you're just rapidly within seconds switching so that you're creating feet-long slugs within the vertical column. It's where you got a change, to introduce a hydrostatic column that is more close to the water than the gas gradient. And this allows you to get the benefits of 3 to 4,000 psi, vertical head to your deployed downhole injection pressure.
Okay. Now, those are all the questions, and this wasn't scripted, but I'd like to give each one of the panelists an opportunity to just make a brief closing statement. We'll start with Ali.
Overall, I think with all of these field efforts, for example, the examples we heard today, it's going to be really exciting to see how they develop over time. And I think I'd like to offer through the national labs that we can help understand some of the fundamental processes that are happening. So I'm hoping that we can have future opportunities to interact and connect and try to continue advancing these technologies.
Kevin, how about you?
Yes, no, I echo some of those same sentiments. I mean, we've been trying to be forthcoming with our project being, certainly not the first time that somebody's injected NGLs downhole or down into a system, but one of the reasons why we've tried to be forthcoming is to kind of what Ali spoke to. We feel like the industry is kind of at this tipping point, and heard a great stat the other day from somebody at Schlumberger where I'm going to butcher it maybe a little bit, but the stat was their view by 2030 is that in a given year, more wells are going to be turning to huff and puff than are drilled in the field. So I think, with a lot of, these industry efforts, as a whole, we're hoping to advance that. And, as I mentioned earlier, we're not arrogant enough to think that, for our project that we've gotten it 100% right or it's the most economic. It's just, been our way. So as we've listened to some of the, possible enhancements we can make that Ali has suggested, or Gordon, making sure that we're always like, taking the opportunity to look at things through a different lens. I think it's all going to make all of our, approaches sharper in the end. So thanks for the opportunity.
Very good. Gordon, last
Yeah.
word from you.
Yeah, thank you. I'll just build on that to really emphasize that it's great to see the change in focus, the interest in terms of sustaining increasing recovery factor. Sure, it's a huge prize. And with that, great to see the major companies, super majors, now starting to identify that as an objective. And clearly the prize is tremendous. And with that, I would agree with the assessment that was presented. As we look to 2030 beyond, the world will change and it will be focusing on increasing recovery factor, taking advantage of the resource base that we've got. So thank you.
Yeah. Well, with that, I'd like to thank you all. I'd really like to thank the panelists. Just fantastic presentations and insights, and both the SPE and ARMA. Thank you for participating today. Thanks, everyone.
Here,
Thank you.
Thank you.
here.
Thank you, Gordon.